Right. So, what we discussed yesterday, we looked at the packing of close packed planes, and we saw how we could actually generate the closest packed structures like face-centered cubic and hexagonal close packed, starting from a linear array of closest packed atoms. Then we built up a 2D layer which is close packed. Then we saw how we stack those two layers on top of each other to get a 3D kind of structure. So that is what we discussed yesterday. And then once again, this is a very common theme, so we'll just go through the what we had discussed yesterday. Here are some more examples of what are known as the interplanar spacings. So here just a 2D set of planes. So before we go to X-ray diffraction, let us clarify these things a little bit. So we can. So like we discussed yesterday, what was interplanar spacing? It's just the shortest distance between a plane passing through the origin and the same plane of that same family, which is closest to the origin. Or alternatively, a simple way of looking at it would be whenever we say a plane HKL, it is not a single plane, but it's always a set of parallel planes. For example, if it's 100 in a cube, then it is all the 100 faces which together form the set of 100 planes, and the shortest or perpendicular distance between them is called the interplanar spacing. So the situation is more clear here. This is a 2D kind of set of planes. Look at this top figure. If this is the origin O, then there should be actually one more plane here. And these are the 1-1 planes. There's no 1-1-1, it's 2D. So the interplanar spacing would be the line drawn from the origin up to the plane, or alternatively we could also call it, this becomes the interplanar spacing. So whenever we have a set of parallel planes, it's the normal distance between those two planes that is called the interplanar spacing. And like we discussed in yesterday's class, these spacings are can be readily calculated based on the Miller indices HKL of a plane and the lattice parameters ABC. So for cubic, what was it? D square equals D equals E divided by square root S square K square plus L square and so on, right? We have those formulae. So likewise, if we go to the other planes, 1-0 plane, the red arrow now shows the spacing for those planes. Likewise, we can repeat for all the sets of planes. And as you can see, depending on the indices of the plane, these spacings are actually different. The absolute value, for example, this spacing is different from the one over here. This one is even more closely packed planes. The 4-bar-1 planes are even more closely packed, and so on. So this gives you a feel for how the interplanar spacings actually change with the HKL indices for a given set of lattice parameters A, B, and C. And in some cases, in fact, you can have an entire material, say a sheet of metal, which can be considered as a stack of parallel planes. So it's a single crystal. If we have a 100 oriented single crystal, if it's a cubic crystal, then you can say that all the 100 planes in that material are actually parallel to the physical surface of the sample. If it's 1-1-1 oriented, then the sample may be considered as a stack of 1-1-1 planes. So that tells you the orientation of the crystallographic planes with respect to the external surface of the sample. So that is called a textured material. Now, how do we deduce all of this? I mean, this was all geometry so far, and that is where X-ray diffraction comes into picture. So how are these crystal structures determined? There's a question. Now, we often have heard of X-rays. We go to the medical doctor whenever there is a problem. We get an X-ray done, chest X-ray, bone X-ray, and so on. So essentially, whenever any material is bombarded with an incident beam, X-ray beam, in most cases, the beam can get transmitted X-ray beam. And this is the beam which is used for our medical purposes. We get an X-ray and then we see what is wrong inside our body. But if it's a crystalline material, if it's a crystalline metal, for example, we also get what is known as scattering. So scattered or diffracted X-ray beam, which is in another direction to the incident beam. And it is this scattered X-ray beam which actually helps us in knowing the crystal structure of the material. So it is the intensity of the scattered beam and its direction with respect to the incident beam, which tells us quite a lot about the crystal structure of the material, particularly the interplanar spacings in the material. So how does this work? So at a basic level, when here we have an array of atoms, whenever an incident X-ray beam interacts with atoms in a material, the atoms inherently scatter those incoming X-rays in various directions, such as shown by the arrows surrounding each particular atom. And this actually happens in all possible directions as shown in the figure. Now, of interest to us is whether we get a strong scattered or diffracted beam in any particular direction as shown by this red arrow A. Now, if that happens, then it's a signal that there is, so as you know from physics, if there's constructive interference between two waves, then the beam amplitude will get stronger. So if we do see a diffracted beam from a material in a particular direction A, then that would really depend on having constructive interference between the X-ray beam scattered by all atoms in the material in that particular direction A. So that is the basis of X-ray diffraction. It's constructive interference between scattered X-rays by all atoms in the material. So how do we use it to judge we are not talking about planes yet. So how does this help us with knowing crystal structures in the material? And the famous scientist Bragg, actually they were father and son, both Braggs, they showed that whenever we have, suppose this block is a material and this red incoming arrow is a X-ray, incoming X-ray. So whenever that material shows a scattered X-ray beam, such as this one, then in fact we can always consider this X-ray scattering, we can always imagine this scattering as happening from a particular set of crystallographic planes inside the material. And that actually happens in such a way that the angle made by the incident X-ray beam with those set of planes, theta, happens to be equal to the angle made by the scattered beam with the same set of planes. So that angle is also theta. So it would be kind of analogous to what we often see in optical reflection. If you have a polished mirror, if you have a mirror or polished surface, and we shine light on it at a particular angle, then the reflected light also happens at the same angle. So this is the kind of analogy between X-ray diffraction and optical reflection, which was first shown by Bragg. They essentially showed that whenever we have an X-ray scattering, we can always find a set of crystallographic planes in the material such that the X-ray scattering can be thought of in a manner similar to optical reflection that happens from regular surfaces. By that we mean there is an incoming X-ray beam at a certain angle theta, and there is a scattered X-ray beam which also makes the same angle theta with this set of HKL planes, with some set of HKL planes inside the material. So this really paved the way for scientists to discover and further study crystal structures in a material. And of course, all these planes are populated with atoms, like I've shown here. I've omitted them just for the sake of clarity. So this is really the crux of X-ray diffraction, and we'll see how this actually helps us in knowing the crystal structure of a material. Now, one key point is, please note that the angle made, that theta, is actually with a set of parallel planes, and unlike optical reflection, it is not with the surface as such. So for example, if we have an incident beam over here, this is the incoming X-ray. And now it makes some other angle. It's different from the earlier theta that we saw in the previous figure. Now this is at some other angle. And let that angle be, say, theta1 to this surface. And if we see such a beam in some other direction, then even then we can actually show that even for this particular condition, the incident X-ray, the diffracted X-ray are once again related by the reflection geometry to some other set of planes, H prime, K prime, L prime. So in this case, there's another set of planes which is now not parallel to the surface. So that's why this angle made theta1 is now with respect to the plane. Sorry, this should not be, okay. So this theta 1 is with respect to the new set of planes H prime, K prime, L prime. So the point once again is whenever we have an incident beam and a scattered X-ray beam, we can always find some set of planes in the material such that the incident beam, the scattered beam, and those set of parallel planes form what is known as the reflection geometry. So here we do the plane normal. So this angle theta 1 is now equal to theta 1 on the other side. So this concept really helps us in finding the crystal structures of materials. So quite a lot of thanks to Bragg, who actually showed us that this is how X-rays interact with crystals in a material. And this is very useful when we come to looking at or examining crystals with the help of X-rays. So I'll just try to tell you the analogy with optical reflection. Like we know in optical reflection, we have an incoming beam of light, then there is a reflected beam of light, and normal to the surface, they are all coplanar. Also, the incident and reflected beams make equal angles with the external surface in optical reflection. Likewise, there is an analogy here, also in case of X-ray diffraction, that the incident X-ray, the diffracted X-ray beam, and the plane normal are coplanar. Also, these incident and diffracted beams make equal angles with the set of planes. So that is the key distinction, that those angles are with the crystallographic set of planes and not with the physical surface itself. That could be at a different angle. Note, however, that unlike optical reflection, the angle theta is with the set of planes and not the surface as such. Hence, the angle made with the surface can be different from that made with this set of planes naturally, unless it so happens that the set of planes is directly parallel to the surface itself. So if we were to rotate this like we saw in the previous figure, if we had another set of planes here, then we have the same beam coming, for example, the theta would change, that would be some other theta, theta prime. Once again, we would have another theta prime, the plane normal would be here. Now, obviously, the angles made with the surface are different from the theta prime made with the internal planes inside the material. So that's the key distinction between X-ray diffraction and optical reflection. So it's not just a surface reflection. That X-ray diffraction happens because of scattering by the internal crystallographic planes, which are filled with atoms inside the material. So that's the key difference, and that is what actually helps us in analyzing crystal structures of materials.
Sir,
yes?
Can a single surface contain two different types of planes, as you explained it?
Sorry, your voice. Yeah, could you repeat?
Can two different types of planes lie on a single surface?
Yes, two different types of planes lie on the same surface. Okay, so yes. So you are saying, suppose we have a surface here, and we have two grains, one with some HKL, and there is another grain with some other HKL. Is that what you mean?
So whatever you have drew here,
yeah,
and I mean both of them are on the lying on the same surface, or are they on different surfaces?
No, I'm just in this case I've just shown. I mean, they are not on the same surface, so I'll just go back one slide. Okay, for example, we had here one sample or one grain. So suppose this is a sample where we have one set of HKL planes which are all parallel to the surface. Now there is another set of HKL planes in the same material. For example, it could be in the same material. And supposing this H prime, K prime, L prime is a different set of planes in the same crystal, but naturally that now won't make the same angle with this surface because the crystallographic orientation is different. So now the point is, if we also want to generate a scattered beam from this other set of planes H prime, K prime, L prime, then we'll need to, I mean, if that happens, then the angle made will be different. That angle will be now be theta 1 with respect to this set of planes. So this theta 1 is now not with respect to the physical surface which is here. This is the physical surface. Yeah, that can be, those two sets of planes can be in the same crystal. Yes, you're right. But the point is that the diffraction geometry, those angles made by the incident and the scattered beams are not with strictly with this physical surface, but they are with the internal set of planes. That's the point. Is it clear? Yeah. So you can have the same crystal having two different sets of planes. So we'll need to tilt the crystals in such a way that this diffraction geometry is now satisfied. So initially, if we had diffraction from the HKL planes like shown here at an angle theta, now we tilt the same material so that the other sets of planes, this condition is now satisfied. That the other sets of planes now make an angle theta 1 with the incoming and the scattering directions. So we'll see that, I mean, this theta 1, this diffraction angle is actually closely related to the spacing of the planes, and that's called the Bragg's law. We'll come to that in a moment. And I'll show you. So yes, you can have different planes. Obviously, you'll have different planes in the same material. It's just that the angle needed for scattering or diffraction to happen from different sets of planes in the same material will be different from each other. So different planes will have their own angle of scattering. That's the point. So it doesn't matter what the angle is made with the surface of the crystal by the incoming X-rays. Now this really helps in crystal structure studies, Bragg's law. So what we have here is I have shown crystallographic planes. This is plane 1, plane 2, and this is plane 3. Set of parallel planes. This is your incoming incident X-rays, ray 1, ray 2, and these are the scattered X-rays. So ray 1 gets scattered as ray 1 prime, ray 2 gets scattered as ray 2 prime. And like we discussed, if we really are getting a strong scattered beam from this particular set of planes, then what it means is this ray 1 prime and ray 2 prime must be exactly in phase. They must be coherent. There should not be a difference in the kind of phase. So that's why we get superimposition, and that's why we get a coherent beam, a strongly scattered beam. If they were out of phase, there will be destructive interference, and the intensity will go down almost zero. So for that to happen, we need to look at the path these X-rays are following. Ray 1 comes here and meets the first set of planes at point A. Then it gets scattered in this direction. Ray 2 also follows the same path, and up to point B, both ray 1 and ray 2 have the same path. Likewise, on the scattered side, after point D, ray 1 prime and ray 2 prime are once again following the same distance. Whatever path difference arises between these two rays 1 and rays 2 is actually this length BC and the length CD. So the ray 2 is traveling an extra distance given by BC plus CD inside the crystal. And now much would depend on how much that is changing the phase of the X-ray by that path difference. So we just click that. So for diffraction to occur, rays 1 prime and 2 prime should be in phase. So the path difference, like I just spoke, is actually given by 2d prime. Okay, this should be sine theta. Sorry, I missed that. If you just do the maths, the path difference BC plus CD should be 2d prime sine theta. Now, if we want these two rays 1 prime and 2 prime to be in phase, you can imagine that if they're shifted by one full wavelength lambda, they'll be run business. Then we won't be able to tell the difference, and the two rays will add up. But if they're out of phase, then there will be destructive interference. So that tells you a simple, in terms of basic physics, that this path difference should be related to an integral multiple of lambda. It should be n lambda equals 2d prime HKL sine theta. That's it. For a strong diffraction to occur from this set of planes. And if the two if they are mismatched by any amount, these two X-rays, then they won't reinforce each other. In fact, there will be destructive interference. We don't want that if diffraction is to occur. So, if there is some path difference BC plus CD, that should be related to an integral multiple of lambda. So that once again the two rays remain in phase, and only then we will get this diffracted beam, and this is the what is known as Bragg's law. And n is an integer called the order of reflection. It can be 1, 2, 3, so on. Now, this actually helps us in really finding the interplanar spacings D in a crystal. Now, we won't get into too many details, but this law can be further simplified. Now, this factor n, this order of reflection, can actually be absorbed into this D spacing itself. So, there are a bit more complex concepts linking the order of reflection to the interplanar spacings of parallel planes. And at least for our work on crystallography, we will consider n to be equal to 1 based on these arguments linking the order of reflection n to the spacing of parallel planes. So we can further simplify this Bragg's law to the one shown here, in highlighted in green, lambda equals 2 d HKL sine theta. So if we have a plane HKL set of planes showing diffraction, then the interplanar spacings d HKL can be related to the diffraction angle theta and the wavelength of the incoming X-rays lambda by the simple relation known as Bragg's law. Lambda equals 2d HKL sine theta. So this really was a kind of breakthrough in crystallography, the discovery of this law by Bragg, father and son. And that really helped us analyze crystal structures the way we talk today, like this is body-centered cubic, this is tetragonal, and so on. All of this was possible because of the advent of X-ray diffraction. So is this okay so far? Then we'll move to actually seeing how this is used for knowing the crystal structure of a material. I don't know, maybe this was covered in your JEE physics, probably?
Yes, sir.
Yeah, okay. So I just wanted to know if it's, yeah, it's not all too new. Okay, so you know it, good. Now what happens is, how do we deal with real materials? I mean, it's all fine. Suppose we have crystal orientation in the real materials. Now here's a polycrystalline sample I have shown, just a schematic. My drawing is not great, but I imagine these are actually crystals in the material. Now we'll talk a lot about all these lattices and atoms and real crystal structures. So we actually take this pen, for example. It is, if you look at it under a microscope, you'll find that it is made up of many individual crystals. So they are also called grains. And most materials that we see are often polycrystalline. By that we mean they are made up of crystals or grains which are oriented randomly in 3D space. So if this is just a slice through material, we'll see this is say grain 1. This would be grain 2. And this will be grain 3. So for example, just by a random chance, it can happen that in grain 1 we have the set of planes H1, K1, L1, which are parallel to the physical surface of the specimen. In the other case, it may be another set of planes which is H2, K2, L2, which is parallel. The spacings will be different. These are planes with different indices. And yet there may be some other plane H3, grain 3H with H3, K3, L3, which is not even parallel to the surface. It's at some other oblique orientation with respect to the physical surface of the sample. So that's the basic scenario. That's if we look at any random material, then that would be the case. Of course, there are single crystal materials like I told you before. Single crystal silicon is used in electronics industry. So if this is silicon, for example, people deliberately prepare materials which have certain planes. It's all perfectly aligned such that your physical specimen can be considered as a stack of, say, this may be all 1, 1, 1 planes. So this would be your D spacing between those planes. And this would be a physically thick, the sample itself may be of the order of, say, millimeters or centimeters, so on. This would be a thick sample. So there are certain uses also for these single crystal planes. You also need it for turbines. If you want to maximize high temperature performance in a material, then there are certain planes which are desirable. If you want to optimize magnetic properties for electrical steels used in transformers or motors, then we want the 001 or the 100 planes parallel to the surface of that electrical steel. So if you have a thin sheet of metal, it's designed such that all the planes are parallel to the external surface of the sheet. So those are known as textured materials. But in general, this is a random polycrystalline material, what I've shown here.
So,
Yeah.
sir, I just wanted to ask, even if this is a pure substance and we are saying that this is a polycrystalline sample,
Yes.
each of the individual crystal will have the same crystal structure, right?
Yeah. It's just the same crystal structure. It's just that they're oriented differently. Sorry, I kind of jumped the gun just in order to tell you, when this is the concept of microstructure of a material. But in order to explain X-ray diffraction, this becomes a bit essential. So suppose I have a large, just imagine we have water and we are cooling it below 0 degrees centigrade. And the free energy transformation, as you know, ice will become the preferred phase. So ice crystals will start growing in water at random locations, and then they will start impinging upon each other. Now, all those ice crystals have the same crystal structure, but it's just that they're oriented differently in space. So for example, I will draw a figure here. Supposing we have initially it's a liquid, just imagine. We cool it below its melting point, and what will happen is, supposing the crystals that grow are cubic crystals. I will just draw some simple cubes for you. Okay, I will just change the color, right. So here is one cube, this is grain number 1 or crystal number 1. Simultaneously with its 100, then some other crystal might grow in some other direction. This will be 100. There's another guy growing here, this will be 100. At some point they will start impinging upon each other. So there may be one plane, for example, this will be 100 set of planes. There may be another crystal growing here with the 100 planes will be oriented differently. So it's the same cube, but it will be oriented randomly in 3D space. And that is why you can have different orientations of the same crystal with respect to the external surface. So for example, if this is this is 100 plane, if I take the same grain and rotate it such that now the 111 plane becomes parallel to the surface, that's possible. Is this clear?
Yes, sir.
Yeah, good. So this is the status. Whenever you look at any material, very rarely we would have perfectly aligned all crystals with the same orientation. In fact, we need to work extra hard to do that, to get single crystals or really textured materials with preferred orientation. If you take a random piece, if I section this pen and look at it, this is what we would see. Grains all randomly oriented. They may be the same crystal structure, but they are oriented differently. So it could be a 100 face which is parallel to the surface. It could be 111. It could be 2211 and anything. So then that brings us to the question of how is X-ray diffraction performed. I mean, if I have there are many ways of doing it. I will just explain the most common way, most convenient way. And once you come on campus, you can actually get a chance to see the X-ray diffractometer we have in the Palora campus. So there's something called a theta to theta scan. So what we do is we have an X-ray source here on one side. It's a gun. Electrons come and hit a target and they emit X-rays, and those X-rays are made to fall on the specimen here. S is the specimen. And what we do is we maintain a particular geometry such that the angle made by the incoming beam with the specimen surface, theta, is also the angle made by the, okay. This is what we maintain. There is another detector. Let me explain it first. So we put another detector. C is the detector, and this is the X-ray source. This is the specimen, and we align everything in such a way that if this is the plane of the specimen, then plane of the specimen, by that I mean the external flat surface. So specimens do need to be flat in order to do X-ray diffraction. So here is an X-ray source. It makes an angle theta with the surface of the plane. And we have put the detector in such a position that if we draw a line from the detector to the specimen point here, S, and that would also make the same angle theta with the surface of the specimen. So this geometry is first of all maintained. And this 2 theta is known as the diffraction angle. That is just the angle between the dotted line which shows the X-ray beam had it traveled straight along this incoming direction. It's the angle between that incoming beam had it passed through the specimen and then the angle that it makes with the diffracted beam. Let's not worry about that right now. Let us see how this actually works first. So the sample is now, supposing I have a polycrystalline sample, or even if it's a single crystal, doesn't matter. We put the sample into stage, we put it in position, and what we do is, as you know, lambda equals 2d sine theta. So different planes would have different d spacings, right? DHKL for the cube is equal to a divided by. So if I have a 1, 1, 1 plane, that spacing of 1, 1, 1 planes will be different from 1, 0, 0 and so on. So we have different planes have their own d spacings. So what does it mean? Our incoming X-ray source is fixed. It's a monochromatic radiation. We can use copper K alpha, for example, which has 1.54 angstroms wavelength. It could be something else, but typically, let's say we are using copper. So lambda is fixed. So that means depending on which plane we are looking at, we'll get different diffraction angles theta, right? And that is why we need to be in a position such that we are able to scan a whole range of thetas that would possibly cover all possible crystalline orientations inside the material. That is why we start off with some small, and we put the sample in mechanically, put the X-ray source on one side, keep the starting angle theta as say 10 degrees. Then what we do is tilt the sample through some small angle theta, and then tilt the detector also by a similar angle, but that will need to be double 2 theta, so that the incident beam and the line connecting the detector to the specimen surface once again maintains the same geometry, that is the same angle theta. So that is why it is called a theta to theta scan. We start with some angle, have an incoming beam X-ray. So if I have, this is incoming X-ray, I had some initial angle theta, then I have the same geometry theta. Now I tilt the sample around its own axis by some small amount, say delta theta. So the new situation will be, this becomes theta plus delta theta. But in order to keep that same angle theta plus delta theta between the detector and the sample surface, I want this to be theta plus delta theta. That's why I will need to tilt the detector by 2 times delta theta, just to do with the geometry. Hope this is clear? Why we need to
Yes,
tilt?
sir.
Yeah, good. Because we want the plane, surface of the plane to always make the same angle with respect to the incoming X-ray source and the outgoing detector line. So that's why otherwise we won't be able to scan different values of theta. Remember the Black's law. We need to maintain that reflection geometry. So what we now do is physically put the sample, set the machine at some angle 10 degrees, tell the machine to go scan the whole range of theta values between say 10 to 40 degrees or 50 degrees or so on. So or even 80, 90, I mean, it depends on the material. So by having this geometry, we always make sure that the incident and diffracted beam, if any, will always make an angle theta with the specimen surface. Now the machine actually scans the whole range of theta values and trying to capture any possible reflections from grains or crystals in the material that may be favorably oriented, such that they are in a position to give a diffracted beam. So the key point here is favorably oriented planes. Not all grains will be in a position to diffract. Because of this geometry, only those planes, only those crystals where the planes are parallel to the surface will be able to satisfy this reflection geometry which we are imposing on the material. So if a particular grain finds that it has a certain set of HKL planes parallel to the surface, and then it happens that the incoming X-ray beam is at the right Bragg angle theta, and by the geometry we are also putting the detector at the right angle theta, then yes, we nicely detect the diffracted beam coming from that grain. So by scanning this whole range of theta values, we are trying to capture the different reflections coming from different planes in the material, basically. And now the readings, so what do we measure? The detector actually measures whether there is an incoming, whether there is a diffracted or scattered beam at any given value of theta. So that's it. I mean, so we basically tend to get a what is known as an X-ray diffraction pattern, where we have intensity on one hand and the angle 2 theta on the other hand, and we just note the intensity as a function of the angle theta. Is this part clear to you? Or I hope this is okay. Yeah.
Yes, sir.
Okay, good. And just note that not all planes, the key point to remember is that not all crystals will be in a position to diffract. That's the only thing that we need to remember. Because we are scanning, we are continuously varying theta. If there is a grain inside which happens to match the diffraction condition, it will diffract. But if there is some grain, which is say this way, it may still diffract at its own diffraction angle, but the geometry imposed is such that the detector is now not in the right position to capture its diffracted beam, because we are imposing this theta to theta geometry. So the only ones whose diffracted beam will be detected are those crystals who have favorably oriented grains which are parallel to the specimen surface. That's it. We don't go too much into that. This will be more for the structure and diffraction advanced courses. So what we do get is here, for example, here's an example of X-ray diffraction data. Here's a lead sample. So we change the diffraction angle theta, and then we actually see different peaks. So there's a strongly reflected beam at particular diffraction angles theta. So we see this is the, for example, there are smaller peaks. This is the strongest peak, and so on. So what we note here is we note the angle at which this happens. Now please note that the diffraction angle is always quoted in terms of 2 theta and not theta. So when calculations, we need to be aware. We need to kind of take this into account when we put values into the Bragg's law, lambda equals 2d sine theta. So this is of the diffractometer. Because of the diffractometer geometry, the angle quoted on the x-axis is 2 times theta. So what we do is just convert that into theta, and we know the incoming X-ray wavelength lambda, and we simply calculate the d spacing. So the angle of diffraction theta tells us the d spacing of any particular plane. But the key question again is, how do we know which HKL plane is diffracting? We know that there is some plane which has caused, and that's the spacing of that plane. We'll get some value for the d spacing based on this. Again, this plane will have its own value d2. But how do you know what planes are those? We just know the numbers, just the spacing. How do we know it is 111, 200, or anything else? Now here is where there are certain rules of diffraction which come in handy. Now it is found that depending on the kind of crystal structure, a lot depends on the particular combination of the HKL plane indices, which decide whether or not we will have a diffracted beam at all. Okay. So thus there are certain rules of diffraction depending on the crystal structure. And what are those rules? Again, this is just to give you a flavor. For example, if you have a body-centered cubic crystal, then there are certain rules like H plus K plus L, the indices for any crystallographic plane, should be even. So that means the reflection indices for the first 6 planes should be, you can be deduced to be something of this kind. Like for FCC, we'll have their own HKL combination. The planes allowed, the planes which actually show diffraction will be different from that of BCC. Like for simple cubic, all possible combinations of HKL are allowed, and so on. So this is how people actually try to identify which planes are actually causing this diffraction. So that's the question then, how do we use these rules? Now we can actually deduce the crystal structure based on the reflection rules. Remember that for cubic lattices, d HKL equals A divided by square root. Okay, fine. Bragg's law says that lambda equals 2d HKL sine theta. Fine. So that's why we can now combine these two equations and write this as sine square theta equals lambda square by 4a square into s square plus k square plus l square. So what this tells us is, whenever we are presented in with any diffraction pattern, we can actually get Okay, we already know the allowed HKL reflections for each crystal, like we just saw on the previous slide. Supposing we have a crystal and we don't know its structure, and we are asked to identify the crystal structure. The peak spacings for those particular angle, the peak positions for those angles, diffraction angles theta, will tell you their absolute D spacing values. That is known. Now what we need to do is, for example, look at the sine theta values for each of those diffracted peak positions. Take the sine square theta values, and there's something interesting which is coming up from the next slide. Okay, so from the reflection rules, we now know the values of HKL. Fine. So since the HKL indices are fixed, the allowed ones are fixed for any particular crystal structure. For say simple cubic, we saw all HKL are allowed. For BCC, there was something else. So like I showed in the previous slide, this HKL combination can actually be correlated with the sine theta squared values. So if we just note the values of the sine theta for each particular peak, square those sine theta values and take the ratio of the sine square theta values, that will tend to follow a certain pattern. So all simple cubic crystals, if you are presented with any simple cubic crystal, we just note the value of the diffraction angles, take the ratio of the sine theta squared values, and that will always follow this particular numbers 1, 2. There will always be in that ratio 1, 2, 3, 4, 5, 6, 8. For BCC, the ratio will be different. For FCC, the ratio will be again different. So taking the ratio of the peak positions, that is the ratio of the sine the diffraction angle theta, take the sine of that, square that angle, and take the ratio of those sine square theta values. That will immediately help you to identify which crystal system your new material is. So this ratio tells us the crystal structure type, and Bragg's law tells us the absolute D spacing, lambda equals 2D sine theta. So the peak position theta will tell you the D value for each particular crystal. And then there's something else we can do with X-ray diffraction. Once we have the D spacings and we know the crystal structure, for example, if it is cubic, then we can very well estimate the lattice parameter A from this D spacing. So we get A equals D HKL into square root of H square plus K square plus L square. That tells you the lattice parameter. So we have completely characterized a new crystalline material in terms of its crystal structure, its D spacings, and its lattice parameter A. And as you know, there are well-defined relations between the lattice parameter A and the atomic radius. So in simple cubic, we saw 2 times radius equals the lattice parameter A. Again, BCC has its own relation between lattice parameter A versus atomic radius R. We saw in the previous slides there are well-defined relations between that. So we can actually also estimate the atomic radius using X-ray diffraction. In fact, that is how it's mostly done, because we can't directly see an atom. So this is one way we can actually deduce the atomic spacing. So this is really quite a very powerful tool of analyzing materials. And I mean, you don't need to worry too much about the sine square theta for the exams. This was just what I wanted to tell you to give a complete flavor for the use of X-ray diffraction. We'll mostly focus on using Bragg's law and then connecting it with the lattice parameters. That should be enough for this particular course. So are there any questions on this? Or is it reasonably clear? Okay. Now, all of this, we should thank the father and son duo, William Bragg and William Lawrence Bragg. And they won the Nobel Prize in Physics in 1915 for their services in the analysis of crystal structures by means of X-ray. So these two gentlemen showed how they derived Bragg's law, and that was really a big leap forward in analyzing crystal structures using X-rays. And it is difficult to imagine what our state today would have been had it not been for the contribution of these two geniuses. And that's why we today can confidently say that iron is body-centered cubic and other things. So I think that closes the bit on X-ray diffraction, and it's almost time up, right? We will start with the structure of alloys in the next class then. So let me know if this part was clear. Otherwise, we'll see you in the tutorial today. Everything okay?
Yes, sir.
Okay.
Yes, sir.
Good. Let me know, mail me if you have any questions. I'll be happy to. It's such a large class, I can't interact personally, but if you have anything, let me know.
Hello, Professor.
Yeah,
Yeah, can I end the session, Professor?
good. Yeah, there are no questions. We can stop for today and see in
Yeah.
the tutorial. Sure.
Thank you.
Thank you. Thank you.